Okay, good morning. So I know it's pretty cold, but I think we got a pretty big class, pretty full class. And last lecture, actually, one student raised a very good question, say whether we should count the class attendance. And I think it's a very good idea because it will encourage all the students to come and also join the discussions. Even if it's a large class, I think the discussion, you are here is different, from you just watch video. Okay. Then I thought about it. I think we need to change this grading policy a little to give a little distribution to the class attendance. So you see, I changed the slide. Only one thing I marked red is the thing we changed. Of course, by changing this, we have to give these 3 points. Then other items should be reduced by 3. So what we did is this. We pick up this class attendance as 3%. Okay. Then the original survey and the class presentation, we make it 12%. Okay. I think it's still we got enough scores to award the student who did a good work on the survey. Okay. And I don't want to make it too harsh. I just say we allow you to have 3 classes missing because some student may have interviews or may have deadlines or may need to go to some conference to present their research work. So we say 3 grace period. It could be okay. Okay. That means starting next week, not this week, because we haven't set up policy yet. Okay. The general policy is starting next week, next Tuesday, we are going to ask you to sign up for each class or distribute the sign-up sheet. You find your name, you just sign your name. Okay. Don't sign for others, okay, because we can easily recognize your signature. Okay. So even have a close friend, if he or she did not attend, that's it. We do allow 3 grace periods, right? And then for each 3 classes you miss, that means you miss the 4th class, you will take 1% off. Okay. And here the other, you miss 6, then you miss the 7th, you get another 3% off. Okay. So we will check this, and TA will check your attendance. If you come a little late, okay, suppose you pass the round of sign-up, you just remind you when you leave, you have to sign it. Otherwise, we will count you did not attend the class. Okay. So is this a policy everybody, agreeable? So how many people vote for it? Okay, we get a large crowd. How many people vote against? Okay, so just to give you a reason why you vote against. You say miss the 4th class, you get 1 point, full 1 point up. You want to get a fraction. Okay. So how many people vote for fraction, or we just get 1 full point off? Okay. Let's have one more refined vote. Okay. Simply says we said 1 person for each 3 misses. So we do not want to count it to refine a scale. We just say if you miss the 4th one, you get 1% off. Some people say if you miss the 4th one, you get 0.3% off. Okay. So let's say how many people vote for 1% off? Okay, we still get. How many people vote for 0.3% off? Okay, so we get more people vote for 0.3% off, then we get a detailed counting. Okay, so that's fine. So then this is a policy. I think everybody agrees on this one. We should carry it. Okay. Starting next lecture, I'm going to distribute the registration, the sign-up sheet. just remind everybody you don't forget to sign, because otherwise you quickly, getting down into the penalty, time. So other than that, we just strictly follow our grading policy as we set up before. Okay. So since the policy is fixed, I don't want for any particular student to change on the grading policy. For example, some students blow up the first midterm exam. They say whether I can get a less counting on the first midterm, I get more counting on the second midterm. I say I have to be fair to the whole class. If the whole class vote for this, I want to strictly follow this policy. We don't change it unless at the very beginning you raise the issue, you say, I'm the one, I really want to do this. Most of the students also vote for it, then we can change. Otherwise, I myself will not be able to change it. Okay, they simply say I will not give you a special permission. Okay, so finally, it's graded by computer. I just say, you just follow the rule, you do all the work in details. Okay, there are a few students who send me emails yesterday or the day before asking for getting into the class. I haven't got a chance to look at it one by one yet, because yesterday, on Tuesday, right after class, I actually went to Washington, D.C. I flew out. I got yesterday the whole day meeting until coming back on the last flight. So I won't get a chance to check detail about your request. But general policy is if your GPA is too low, I will not allow you to get into this class. If you are on the waiting list, you probably just to try some other classes. Okay. If your GPA is high, you really have the need. For example, I did give some students who are doing PhD right in the field, in the data and information system field, because if you do PhD, you need to take a PhD qualification exam, and those courses will really help. I give a special permission to those students. Okay, but the other students, I have to check one by one. Okay. So now we continue our discussion on the keynote speech. Okay. The reason I want to use this is I give you outlines to see what we are going to learn, or some essential things we are going to learn. Then you know what are the important things which may help you to do research projects. So this one is very good for giving you good ideas. Say what should be good topics for research projects. Okay. Last time we discussed, we said if we want to turn big data into big knowledge, a very important thing from our point of view is how to turn big data into structured, heterogeneous information networks. And with this big network, we're going to do data mining on such heterogeneous structured networks. Okay. Now we come down, I can give you some simple example. If the data is structured in the network form, actually you will be able to dig out, to compute a lot of things very interesting. Okay. Just to give a simple example, this is the first set of papers. Yi Zhou-San, she worked as a PhD. She worked out some very interesting principles. Okay. One principle she worked out is metapaths and a similarity search in heterogeneous networks. What is metapaths? Okay, the general philosophy is this. Suppose you just get the data like the previous one, like this entry. You get a bunch of authors, you get a research paper with a title, and you get the venue, like Wisdom, and you get a year, like 2012. Okay. So if you think paper, venue, term, and author as four types of entities, they link together in some way, then you construct a heterogeneous network like this. Okay. Suppose we get a paper. Paper may, publish in certain venues, or, written by certain authors. This arrow means citation. That means one paper may cite some other papers. And term, essentially, suppose we only count the terms in the title of the paper. Okay. So this is a very limited data sets, but we can get this data sets like 3 million such data sets actually are stored in the DBRP, which is computer science research publication, like a database. Okay. If we get this, there are some basic functions we want to study. For example, if you study database, you probably know database schema. Schema means actually it's a table header or something. It's basically lay out your structure of your data sets. Okay. Here, that's the same thing. We got research papers. We can work out this schema. Okay. And suppose you want to have similarity search, which is a basic search, because if you do clustering, you do classification, all these somehow related to how to calculate similarity. Like you do clustering, you say these two authors or these two papers should be clustered together. You must think about similarity. They are very similar, that's why you get them together. Okay. Suppose we want to say who are the most similar. That means the most similar authors to Christos Faloutzos based on the DBRP network. DBRP actually is Computer Science Research Publication Network. Actually, originally, they only took database and logic programming research publication. That's why they call it DBRP. Of course, now they take everything. Okay. Then this one, they changed the name called Digital Bibliographic Library Project. Okay, so that's essentially it's a computer science, digital bibliographic library, essentially the research publication database. Okay. The interesting thing is, if you just ask me, say, who are most similar to Christos Faloutzos, who is a professor in CMU, okay, there could be many different kinds of understanding. You can think about who are most similar to him. Maybe his brothers. Okay. Actually, his brothers, there are 3 Faloutzos published a very famous network paper we're going to introduce. The author said it's Faloutzos. Actually, the Christos Faloutzos is the first one. Then his 2 brothers are also computer science professors. But you definitely say, I do not mean the DNA similarity, right? What I really mean is the author similarity in some context. But the context, you can represent the context based on some meta level. What is meta level? That means you based on the schema. You can say, what is similarity? I can give you one kind of similarity is author, paper, author. That means if they share common papers, that means they co-author papers. That's the reason you get one author, you link to this paper, another author also link to the same paper ID. To that extent, if you say your metapath is author, paper, author, okay, then what do you get? This is basically based on the PASSIM formula. You compute, you will say, I got this most similar authors ranking. Of course, Christos Faloutzos is most similar to himself because, that's obvious. But then you look at the others, like Spiros Papadimitriou, Jimon Sen, or Yuri Leskovic. Actually, those are all professors in different universities, but they graduated from him. Simply says he was the advisor. They got lots of papers together. If you think about it, common co-authors very likely are the close collaborators or students' advisors, right? So you get this similarity. Actually, it's not strange. It's very expected. But if you look at score of similarity, they are not so similar. Why? Just because Christos is a senior professor, he probably got like 500 papers. Okay, but Spiros, when collaborating with him when he was doing PhD, probably only get 10 or 20 papers. So the similarity on this actually is still very small. So that's what you can expect. You will get this similarity. But if you say, no, I don't mean this. I don't mean, they are similar just because they are professors and students. They are similar may mean they are all published in the similar venues with many papers. That probably is the similarity. If you do this, you probably can see that a student did it a few years ago. Actually, the most similar one is me, Rakesh Agarwal, JMPay, the several people. Why we are so similar? If you look at the meta paths, you can see this is author paper, venue, author paper. That means if you traverse, if you do, some people say, well, I do random walk. The difference for this walk with a random walk is, the random walk is any connection, you just walk, if you got a 100 out degree, you just go out with the probability every pass, every exit got a 1/100, right? But here is we follow the meta path to walk. That means if you got an author, you follow the meta path, go to the paper. Even paper has citations or terms, you don't walk that way. You say, from the paper I walk to venue, so I walk to journals and conferences. Okay. Then the other author may also walk in a similar way, in a symmetrical way, they finally reach to the common venue. Okay. To that extent, if you take this one as a meta path, simply says, if I publish, I do not have a co-author paper with Christos, okay, but we publish in the similar venues, the same venue, suppose KDD or Sigma, the VRDB conferences, we all publish in the similar venues, we walk up, we reach the same thing. Okay. If we have many such entries, then we are most similar. Okay. So that's the reason she actually calculated, she put down those ranks just based on the similarity scores. So you probably can see this similarity in a very large data sets. If you follow the meta path to do the walk instead of purely random walk, you actually can control your semantics, right? And actually, you get a better semantics. In the sense, you say the first one, the left-hand side one, actually just follow the co-author one, okay? The other one is sort of follow the co-venue one, okay? Then you really capture the subtle similarity in the data semantics. That's the reason you probably see you may like to use metapaths to control the semantics you define. So that's one. Actually, before this proposal, before Izhou did this, the similarity in the network, most people following sort of like a random walk with restart, or different weighted random walk. But that random walk may be okay for Facebook or for Google, doing PageRank. But if you really look at the structured network, you do the random walk without thinking about metapaths, it's too random. Okay? You cannot control the semantics. Okay. We are going to, yes? Yeah, it's a good question. The question is, how do you calculate this score? Okay, it's a very good question. I'm not going to lecture on this because this one is it's just give you the flavor, say what we're going to learn. Okay, once you get into how to do data mining on heterogeneous information networks, we are going to introduce the measure. The measure actually is pretty tricky. We tried using PageRank, using personalized PageRank, using SimRank. We tried many of them. They do not work well. We work out our own measure. This one actually calculated based on our own measure. It's a very good question. But the question actually is non-trivial. But we are not going to introduce it now. Okay, just know there's some magic we can calculate, we can get out. This measure actually is very interesting in the sense, a lot of measures, just give you a simple example, like a PageRank. Everybody, we are going to introduce PageRank, but I assume everybody knows PageRank because they use Google. Google started with PageRank. Okay. Using our measure called PassSim, pass based on similarity, the measure. A very good thing is PageRank get favor to somebody who has lots of link to it. Okay, that means you have high centrality, you get higher scores. Okay. Then you know there's a distribution we call power law distribution. A small number get very, very high links, like Obama or somebody famous, so get lots of links. But there's a large majority, they have very, very low connections. We call this as a long tail. Okay. For long tail data, in many cases, you try to calculate similarity, you get substantial difficulty because the tail is too big, too long. Okay, it's hard to distinguish them. Okay. But this new PassSim has some magic. You really can distinguish the long tail data. Just give you a simple example. We do not pick up Christos Faloukas because he's a big name in database and data mining. Everybody knows him. Then pick him. Likely you can make it right. Okay. Then we pick up one who is much less known. We pick up An Haiduan. Okay. Why we pick An Haiduan? The first thing is we know him because he was assistant professor first at the UIC. In the same group as other professor, like currently at DTI or Professor Dai. Professor Dai actually joined the department the same year as him. Okay, but he stayed in UIC for just 2 or 3 years. Then he actually moved on. He was grabbed by University of Wisconsin, joined Wisconsin. Okay, then he's not in this department. It's easy for me to take him as a victim, as an example. Okay. I just say, who is most similar to An Haiduan? Okay, he got PhD in 2002. Okay. The interesting thing is he's in the long tail because he's not as famous as Christos, right? And whether we can find it very sensitively, because there are 500,000, actually 700,000 authors in DBRP. Okay. Who is most similar to An Haiduan? Actually, he's in the long tail. You can randomly pick one who is also in the long tail. It's very hard to make it very precise. Okay. But to our own surprise with this measure, we found a Jignish pattern. Okay. If you do not know Jignish pattern, the interesting thing, if you just look at the paper, you probably see. The very interesting thing was now they're working in the same research group, okay, in University of Wisconsin, the same research group. Their PhD was not too far apart. 1998 to 2002. And more interestingly, I was giving a talk in Ann Arbor in University of Michigan. They were all laughing. Okay, why they were laughing? Just because Jignish Patel was assistant professor in University of Michigan. Almost in the same year, 2005. Both of them were grabbed by Wisconsin. Okay, they joined the same group, Wisconsin. So, of course, there are 500,000 authors. Okay, these two, they work on the same thing. They actually exit, one from UIC, one from Michigan, all join Wisconsin. Of course, they are most similar. So everybody was laughing because, of course, these two are most similar. But the key is our system never know this, right? What you know just the research publications. But you really find, based on the co-venue, you really find they publish similar number of papers in the very similar venues. They are very, very similar. Okay. So even the others, for example, Amor Dashband, you see he's also in the database area. He's a professor in Maryland, in the similar years. Jun Yang in Duke University, also in the database area. So these several, you can see Renee Miller actually is a professor in University of Toronto. I could not find her picture. I just did not show it here. But these are the 5 professors. They are very, very similar, which everybody in the field knows that. Okay. So you probably can see. It's very sensitive. You really capture similarity for the long tail data, not just for the the real top guys. Actually, one professor from Stanford came. I could show this result. He said, "This actually is very hard to get. We work on this network similarity. We use lots of compensation. We just cannot get it. Okay, you have thinking about this guy is a long tail, this guy is in the star. You have to think about different parameter, different factors to compensate it. Look at our formula is extremely simple. Okay, this is power of MetaPath based. Actually, he invited me to Stanford his statistic and data mining symposium to give a keynote. So because he found this result is really, really great. Okay. So this is one story. You can see the similarity measure. You use this structured network. It's very powerful. Okay. Yes? Yes. Yeah. Okay. The question is why the long tail ones particularly difficult comparing to the top ones. Because you see the most of the measures, no matter you do the traverser, you do this, everything computation-wise, the one who has more links, in many cases, they get more weights. No matter what kind of measure, of course, we did this measure overcome this problem. But if you think about a personalized page rank, if you think about page rank, why this guy was ranked high? Because there are many things point to it. Okay. So since the stars, you get many, many points. Like you publish many papers in the top venues, you get many, many points point to you. So your center of gravity to calculate similarity is very easy because you have a very small number of people who have so many points point to it. Okay. But once you are in the long tail, there's a very big mass. They have similar number of connections. And they are so similar, it's very hard to distinguish them. So you think about it. If you say Obama and you get another one who is very, very top, maybe another president in some other country, so everybody knows them. It's very easy to do a comparison. But if you say the general mass, you get 100 millions of people, you try to say who is most similar to who. It's not that easy, right? You think about it, you like this. There are 500,000 people. Say, who is most similar to An Haiduan? As he did not publish that many paper, not that less paper. It's right in the middle is a very, very big body, right? So that's the reason it's hard to capture the exact similarity. Yeah, but we are going to learn this. Just give you a taste, a flavor, to say there are some very interesting thing underneath. But I'm not going to open the hood, let you see the engine, okay? But just to give you a flavor. Then another one I'm going to show you is rank class. Rank class means you want a lot of things. You want to do cluster, you want to do ranking. That's almost naturally. You just think about why PageRank is so popular. Just because you actually can rank things. Just to give you a simple example, you probably do not know before Google came what was the life. What's the life of the search? Okay. We went to a conference. That time the web was very hot. Everybody went to a conference on the web or on data on something. Okay. The first thing we want to find some researcher I really want to follow is I ask his name card. Why I ask him to give me the name card is because the name card contains a web address, the URL. Okay. What I do is I take my homepage or somewhere, I get a link to this person. Okay. Then all the other students they want to follow, suppose this is Jeff Orman in Stanford. What do? You put a link there, and the student wants to find his paper, they follow my link, they got it. Okay. And say, why? Why you have to build links? The reason is, if you think about it, suppose Jeff Orman is very famous. He is. Suppose he has, say, 50,000. Actually, it's more than that. You go to Google. 50,000 entries. Okay. You probably know the information retrieval. You build an inverted index. Okay. And he's so well known. He got 50,000 entries. His homepage is right buried somewhere in this 50,000 entries. You know, that's the old search engine. They don't have a ranking. Okay. Who wants to use it? You get 50,000 entries. You spend days trying to find where it says homepage. No, there's no way. Okay. What do? Is there was earlier days, there was a Gopher. Gopher, what they do is you go, if you know Stanford, you go to all the university, U.S. universities, go to Stanford, go to database group, then you find it. That's a long traversing. You remember that time the web speed was not so high. That's why the link is very important. Okay. But what's the major role of Google? Why Google the student got so excited they even do not do PhD, they set up a Google. The reason was everybody said this is a revolution. Why? They can automatically rank pages. Okay, that's PageRank. Once you can automatically rank page in a very meaningful way, nobody wants to do the previous Gopher search. Or Yahoo, actually, that time was very, very well known. What they do is they use human to build the links. Okay. That's very expensive. You think about this. Okay. The computer science people may build it. There are so many different other disciplines. They have to build these links. The human cost is just tremendous. And people can change. You know, they can change anything. So that's the reason ranking is very important. But ranking will only make sense if you find clusters. Okay, just think about it. You know, you say this guy is famous. Famous on what? You know, if he's famous on basketball, he could be ranked very high. Like Michael Jordan, one Michael Jordan ranked very high in basketball. The other one could be ranked very high on machine learning. Right? So that's the reason you have to do clustering and ranking. But the interesting thing is people, in most cases, they do not do the clustering and the ranking together. Okay. This is the algorithm in 2009 proposed by Yizhou Sen. She first said ranking and clustering should go together. Okay. That means if you have a way to, based on these links, you sort of thinking about it, you can group things if they are ranked high, or they are closer together, you can group things. So then you actually will be able to work out very good ranks and very good clusters as well. Okay. So you probably can see this one is, these are set of authors. These are set of venues. How do you do clustering? How do you know these are similar authors or similar venues? Actually, it's very easy. You think about this. Suppose these are the database conferences. These are the database authors. Why you automatically know these are database conferences? Just because there are many, many common authors. They publish in those common conferences, right? So they build links. They automatically, based on links, they group them together. But more than that is there are lots of subtlety. But if you can rank them, you can rank the top venue or top authors. Actually, this cluster will do it in a very clean way because anybody can co-author paper published in some other venues. Right? But if you really cluster them, dedicated one, highly ranked one, then finally this cluster and the ranking will give you very, very good semantics. Okay. You probably do not convince why cluster and the rank should get together. I'll probably give you a simple example. You know, last year, the Turing Award giving to Mike Stonebreaker. He's a database person. He actually constructed the Ingress system, the first relation database system together, in parallel with IBM System R. And later, he developed a Postgres, column-wise the system. There are many, many database engine he created. He got Turing Award. Okay. He's a die-hard database person. If you think about ranking and clustering, you can think in this way. Okay. The first important thing is not every node should be treated the same. Agree or not? Think about this. If Mike Stonebreaker said, I'm not going to do database anymore, I probably will get into, neural networks or something. Okay, that would be a breaking news in computer science, right? The Turing world in database, moved down to neural networks. But that also get a sea change for many, many people, right? You think about all the students and followers. It's a very big news. His ranking high, his impact is high. But if you suppose you are the first year PhD student, you say, oh, I'm not going to do database anymore. I'm going to do neural networks. Does that anybody care? Nothing will change, right? So you can change 3 times a day, but you won't change the whole structure of the research field. Okay. So that simply says, in the network, in anything, not everybody is equal. Okay. Since not everybody is equal, if you really grab the top-ranked one, you put more weight on them. Your clustering, ranking, many things you will do actually better. So that's the general philosophy. She actually grabbed this. She worked out ranking and clustering go in the same loop, in the same EM framework. Okay, I'm not going to give you the detail. EM is expectation maximization. Essentially, it's a clustering loop. Okay, if you can do this in this loop, taking care of ranking and clustering together. Clustering actually is soft clustering. It's a mixture model. You give different probabilities. Then every time you adjust the cluster, you redo the ranking, then redo the clustering. After a few rounds, you get a very little change. You come back, you look at it, you get a very good cluster and also very good ranking, okay, for the objects. I'm not going to show you the computer science results because later you are going to learn it. I just show you some other results using the similar methodology. One result is, I got one student here. Okay, that's a few years ago. He was not doing data mining. He was doing computer vision, okay, in EC department following Professor Thomas Huang. Okay. He was doing research project. He says, this algorithm truly interesting. I'm going to try on the pictures. Okay. What he did is he took the picture as a center. It's more like the research papers. Then he got the features, like you have texture, you have a color, you have different distributions. He took color, hue, texture as the surrounding features. It's like the schema. You get center as not like this one. You get center as research paper, not center as picture. Okay. Then you get surrounding one like venues or keywords. Now he just said these are the colors, texture, hue, and all these things. And then he took hundreds of thousands of digital pictures. And he did a clustering ranking. Okay. Then you probably see his clustering ranking is pretty interesting. You look at this. This is something like a water, no matter it's ocean or lake. Oh, that's the kids, right there. You see all these pictures are very similar, right? Then you look at this one. This one is a night view of DoubleTree if you have a very good sharp eye. But all the others are night view of buildings. So that means you can take picture anytime. I don't care. But as long as you have a similar image, impression, I group them together just because I know there's color distribution, there's a darkness distribution or a structure distribution. And he got a very good collection of the pictures, just doing this. Got a very nice album, right? Of course, it's not album based on semantics on whether this is Miami or this is, Great Lakes. But anyway, you probably can see this is very good. Another interesting study is I got visiting a professor who visited me. He's from University of Queensland in Australia. Then he says, this one is very interesting. I want to do something not just for computer science. I want to do something for medical science. He took the medical research publication, which is called PubMed. Okay? And he took this The medical publication is also structured. You can see there's the article, there's journal, author, treatment, clinical trial, and disease. What he said is he wants to cluster different disease and find the most influential treatments. Okay. And you can see disease is one, treatment is another, and based on all the other links. Okay. And his argument is very interesting. He says, oh, of course, if you are, this is the AIDS, this is, like breast cancer, this is, lung cancer or something. Automatically, based on the journals and based on something, disease names, you can cluster them together. But the more important thing is you can rank them. Okay. How do you rank them? He basically says it's very simple. The most influential treatment will be studied more in the top journals. Okay, you just based on ranking of journals and authors and papers, you just turn it around. And he actually showed in one research paper, he showed many different disease, and he actually, like this one is for AIDS. He lists the top 10 most influential treatment for AIDS. And he just took all his results, went down to his neighbor medical school in University of Queensland, and asked the professor to look at it. They were surprised. Say, how do you know that? There are so many diseases. Your treatment, actually, some are very new, but they are really, really good. How do you know that? He said, I just do my data mining. I got it. So it's a quite interesting story because he published that paper, and many people actually look at it. Even today, I got somebody asking for code. I said, I'm not the author. I do not have the code. You go to Australia. You communicate with that author. But that simply says it really, pretty interesting algorithm, right? Another one is classification. Okay. For data mining, you probably know there are lots of classification methods which play a very important role, like deep learning, like neural networks, support vector machines. There are many things. But now, suppose we got a heterogeneous networks, like all of these linked as, for example, you can see you have authors, you have papers, you have conferences, you have terms. They're all linked together like this. And how we can do good classification for research fields. Okay. The interesting thing is there are several kinds of entities, like conference is one, term is one, paper is one, author is one. You don't have to give label for every kind. You probably just give some kind. For example, I may mark this author as a database author, or this paper is a data mining paper. Okay. What's the impact if I give a small number of labels? Remember, once you give small number of labels, you will be able to propagate based on the links, right? Because this author is linked to this paper. If this author is database author, likely this paper may be a database paper, right? And then this paper linked to the conference may also be database. Of course, it's not sure. It's not 100%. The reason is maybe you co-author with another machine learning one who published in a database conference, right? But on the other hand, you can think about this, the statistics. You get millions of papers. They all link together. You do this propagation. It becomes very reliable. Okay. So the interesting thing is you give some seeds or some labels to some types of objects. You help the whole network, all the types or every node. Okay, you can help. That means you actually use this knowledge. You can propagate down. It will help you to get a very good result. I'm not going to show you the algorithm. The algorithm called rank class classification. The other one is rank class, is clustering. Okay. Intentionally, this student want to use very similar term. It's very hard, very confusing when you pronounce it. But actually, one is rank classification, one is rank clustering. She used, this is Ming Ji now, she's working at Google. She used this one to work out a rank class algorithm and it shows you can, because you have labels, the other one has no label at all. You get more labels, you even can be even smarter, right? So you probably can see, if you know the research field, we have database, data mining, AI, and information retrieval. And that's what she got. She got top-ranked conferences and top-ranked terms. You may watch this to see the quality, okay? I do not know how many people knows. Let's first look at the data mining, okay? Because I need to give you a little information. The KDD is top-ranked data mining conference, which is very true. Then get an SDM, ICDM. They get a PKDD. PKDD is Europeans KDD conference called Principles of Knowledge Discovery in Database. That's a PAKDD, the Pacific Asia KDD conference. So you can see that this ranking is not bad. Okay, it's pretty good. Then you look at the terms. Okay, you can see the term, top-ranked term is mining, data, clustering, classification, frequent. Frequent means frequent patterns or something. So you probably see these are very high-quality terms in data mining as well. So that simply says not only you can do very good grouping to give you very high classification accuracy, but also as a byproduct, you get a very high quality on the ranking as well. Okay, so that's the one we probably say that you use heterogeneous information network, you can do ranking, you can do this very nicely. Another one could be link prediction. You want to predict some connections or some links. Okay. Because this link could be heterogeneous link, so Joe actually called this one as a relationship prediction. It's not exactly a link, because a link in many cases is thinking these two authors, they link together. Actually, you can link this author with this venue or this paper, you can link them together as well, right? So she called it relationship prediction. Actually, this one was triggered by Christos Valoutsas once. I was in a conference, ECML PKDD, give a keynote. He was in the audience. He raised his hands. At that time, I show his name, his picture, say who is most similar to him. Everybody was laughing because he was in the audience. He raised a hand. He said, Jiawei, your system looks very, very interesting. I give you one question, whether you can help me solve. I said, what's the question? He said, can you predict what papers I'm going to write next year? Okay. Of course, I said, you know, I cannot even predict what paper I'm myself going to write. How can I predict what paper you're going to write? So I took this one as a joke. I actually came back. I talked to Yijo. I said, Christos' joke said, can you predict the papers, what papers he's going to write? And she actually was serious. She says, of course I could not predict the concrete title, because you can change the title last minute, right? My prediction was wrong. So, but you can predict what kind of topics he's going to work. He's going to work on data mining. He's working on big networks. He's going to work on the tensor, you know, the scalability on tensors. I'm pretty sure it's very easy to predict. But maybe I myself, she herself said, I myself can work out an even more challenging but more interesting problem is who will be his new co-authors in the next 5 years? I said, that's almost impossible. You do not even know what student he's going to get. How could you predict? She says, I'm not going to predict anything not in the current database. The new students not publishing any papers, I'm not going to predict. I'm going to predict something, those authors already in the database, whether you can find some new co-authors. Okay. Then I thought this could be a very interesting research problem. We started discussing on this. Then the interesting thing becomes this. Predict the co-authors. Essentially predicted this relationship, APA. Author, paper, author. Okay. Then to predict this relationship, in the network, we have many other kinds of relationships. Okay. For example, we may have, this is A, work on this paper, this author work on this wrote this paper. This paper, this arrow means citation. This paper may cite the other paper. That's the author of the other paper. That means if you use this meta pass, essentially say, if you cite this paper, whether you are going to co-author with this paper in the future. Okay. So that's one relationship. We don't know yet. Okay. But maybe somebody cites your paper you may want to co-author, or you may have paper published in the same venue you may want to co-author. There are so many. You think about this. We listed. Actually, because very long paths will not really work well because it's too long, you lose the semantics. We just pick the short paths. The short path means length 3, length 4, these short paths. We just study these short paths. But there are many. Which one will count? Which one will weight more? We don't know yet. Okay. But the interesting thing is there are lots of data in the database already. Based on this database data, you are going to say which role likely will play more. Okay. That means some meta paths probably more important than the others. Can we calculate this? Okay. So she did this. What she did is she just based on, suppose I pick up to 1990, I try to predict 1995, these 5 years gap. You co-author, you wrote this paper, you publish in this venue, and later you co-author with somebody, with maybe that person. What is the previous information trigger you to co-author with this? Okay. Then maybe to your own, common sense you may work out, but we want to work based on the data. What you can see is we did work out a few important we call predicting metapaths, or the metapath has more values. We call 4-star paths. Okay, how do we judge the star? We basically using called word test for logistic regression. Using this logistic regression, we work this out. We found some paths has pretty high p-value. Some has pretty low p-value. If you know statistics, like those prediction logistic regression, you probably know if the p-value is high, actually means it's a little like random walk, right? So you don't really have predicting power. But if the p-value is very small, very sharp, you have more prediction power. Okay, so you probably can see. I first grab one. This p-value is really high. This means this. Okay, if you look at this, what this means. This is the author wrote this paper. This paper cite this paper. This paper cite the other paper. That's the other paper's author. I'm going to co-author with him. Okay, just think about this. Suppose I work on a network paper. I cited Mark Newman, who wrote this introduction to networks. But he's a physicist. Okay, he's a University of Michigan physics department professor. Okay. He may cite a paper by Einstein, say, because of physics, right? So do you think in the future I'm going to work with Einstein? No, it's impossible, right? So you probably see you got to cite this paper cite the other papers. The citation, one paper cite 20 papers. The 20 papers cite another 20 papers. The chain is very, very big, very far. Actually, you lose the real semantics. So it's not a good predictor. Okay. So you probably see that's why you get such a high p-value. It's like a random. Okay. But there are some very good 4 stars you probably can judge. This one means co-venue. That means you regularly publish in the same venue. This is co-author. You regularly co-author with the same author. This is co-term. That means you regularly use common terms. This one is co-citation. You regularly cite same papers. You think about this. If you really do this, likely in the future you are going to communicate to work out same paper, work out a co-author paper, right? So you probably see, just based on this, look at the metapaths, they are very telling. Okay. Then she worked out, based on this, doing the training. Okay. Using training, we are going to predict, some real people, the real future co-authors. Of course, we cannot predict the future, but we can use the past to predict a little, recent past. What we did is I took my previous student, Jian Pei. He already quite well-known, very, very well-known researcher. He actually got an ACM fellow in 2015. That's not so many ACM fellows in computer science. He got it. So he got a PhD from me in 2002. So he just said, I'm going to predict what new co-authors he is going to get in 2003 to 2009. Okay. And of course, there are like 500,000 authors. So who will be the new co-authors? She used this metapath and predicted top 5 potential co-authors in the next 6 years, 2003 to 2009. To our own surprise, actually, some a big name like Philip Yu, everybody wants to co-author with him. So he got like 700 papers or 800. He's in DBRP, his number of papers ranked number 1. Okay, and probably number of co-authors also ranked number 1. So that's the reason, he ranked number 1, nothing strange. But we got somebody even very less known, we did not even know them well, and they got a co-author rank very high. And it's true. All those bold ones is true. That means she predicted the top 5 co-authors. It turns out 4 of them are true. The only one not true is Osmar Zayan. Actually, Osmar happens also to be my students, one of my students. He actually graduated from me in year 2000. Jian Pei graduated me in 2002. They're 2 years apart. And he's a professor also in Canada. Then I just asked once in 2012, he was the one introduced me for the KDD keynote speech. I just asked him, I said, what happens? Why you don't work with Osmar? You don't like him? So he says, actually, your time is too restricted. I actually got a paper with him in 2011, if you check it. So that simply says, actually, the prediction really has a power. Right? You think you really, you took 2002 before data, you can predict 2003 to 2009 co-authors. So it's a little surprising. Of course, he predicted me as well, but not everybody, she predicted I really co-author. But I know every one of her prediction. They are really, in principle, if I was not so busy working with my students, I probably would co-author with them. But anyway, that simply says this really captured the essence of the semantics in the networks. Okay, so it's not only she did this, later there were several students in our group, like one is Xiang Ren in 2014. He actually got a paper using this kind of philosophy. Say he will predict it. For this paper, you remove all the papers. You say for this paper, what papers they are going to cite. Okay, and he actually got a very, very high accuracy as well. That means it suggests the papers to cite. Okay. Actually, Google the other day, one researcher in Google said he read the paper. He said, "Could you, work a little more with us? We probably can put this one as a Google Scholar function. You give a paper, you say what papers you should cite. Probably will help research. If you did not read it, you better read it, right? So that's actually it's pretty interesting. There are many others, like using recommendations or something. But anyway, that simply says the heterogeneous network, you get massive real data, really high quality data. You put in the network, you can make magic. You really can do a lot of prediction, clustering, classification. But the problem is, in the real world, do we have such network everywhere? The answer, unfortunately, is no. Okay, just think about this. The people who spend lots of time get exactly the same semantics like research papers. This is the author, this is the title, this is venue, this is year. You get everything structured. But the real world is not so structured. Then immediately the problem becomes, if we can work on the structured data, how can we turn the unstructured data into structure? Then we can work on it. Okay. That's the game. After Yi Zhou-Sen, she got a dissertation award. She graduated, became a professor. But now we, the remaining team, actually are cracking on a more difficult problem, is handling unstructured data. That means, suppose you give me newspapers or video, scripts or something. Can I really understand it? Can I build a network so later we can do prediction? Okay. So that's the problem everybody would love to work on. Actually, yesterday I was in Army Research Lab. We did a demo. The demo is very exciting if you really think about this. We took lots of news articles. We put it in. Okay. The news article has pictures, has short videos, some in the YouTube, some in CNN, but they have some kind of a scripts. Okay. But nothing is really structured. You put it down there. Then you probably want to say, I want to find, say, demonstrations, maybe in Baltimore in 2015 or something. You wrote down this, they immediately show the video. The interesting thing is there are so many articles related to this. We can summarize them automatically. We show the general headlines on the part without reading this 1,000 articles. We can show the general summary or most important things and show it there. It's more like a really CNN headline. You read it, it does make a lot of sense. Okay, can we do this? That's the game we are playing. We actually work out this demo. I got very excited because Heng Ji, the other professor, her team in RPI, they actually did not even have a break for Christmas and New Year. They got the whole team actually work during the whole winter break time. They made a very impressive demo. Then you show those video, and then they automatically partition this, say this is a burning car, this is a riot police. They really can. The interesting thing is they even write down, say, riot police instead of, say, these are the people. Okay, and how can you do this? Okay. But that's the one. Actually, that's the technology we are developing. Okay. So let's say, what is a game? Okay. That means we start from the text data. Of course, we would like to start with multimedia data as well, with some kind of scripts. Okay, that's also text data, you can think. But we have some word knowledge, like a Wikipedia, Freebase, Yago, or something. There are lots of them. Okay, that means we are not came from Mars. Okay, we do have some word knowledge equipped, but we don't want people to explicitly mark some sample documents. That's the most NLP and machine learning people are doing, is you mark, explicitly take those sample out of these newspapers, you mark them, ask experts or human, mark non-trivial one, for example, 500 documents or 20,000 queries, okay, to link them, which actually is too much. We want almost automatically getting those keywords out, phrase out, entity out. Then we can construct networks. Using this network, we can mine knowledge out of it. So that's the whole roadmap. Okay. But it's a nice roadmap. You have to work out every one by one, you really solve this problem. Then you can claim, I can turn the unstructured data into structured knowledge. Okay. It's a big game, but it's an important one. Okay. Now we see how we do it. The first important thing, I put the light bulb, means there's some interesting philosophy, new ideas. Okay. One idea is we don't want extensive expert labeling and curation. That means a lot of people are doing is, you give me data, I will ask expert to put a lot of marks. They call it curated data. They rely on those curated data, they do the subsequent work. But that's too much. You think about this, okay? You got a 2013 New York Times you curated. But it doesn't work for 2015 because 2013 things were not repeating in 2015. 2015 has something much more different from 2013. You have to curate it again. That's too much. Right? Then you think about it. You curate this. Can you use it for computer science? No. Can you use it for medical science? Definitely not. Right? So you can see every field, every corpus you curated, how much cost for human. That's not realistic, right? So what we want is we want to explore the power of the massive text corpora by itself. That means the data may tell more if we work on it. We're not trying to understand one article, but you give me millions of them, I will build the correlations, build lots of things. Then I probably can understand a lot of them. Okay, so let's see what we are doing. Okay. So the first interesting is phrase mining. Okay, the phrase mining means we do not like single word. We like a bigger semantic unit. To just give you a simple example, yesterday I was in the airport. In the airport, if I talk to people, say United, they say over there, okay. There's no ambiguity because United means United Airlines. There's only 3 big airlines left in the US. You say United, of course United Airlines. You say American, it's American Airlines, right? But if I go to United Nations and say United, okay, you probably really get confused. What do you mean? Because it could be United States, United Nations, United Kingdom, United Arab Emirates, or there are so many. United Parcel Service, right? I want to get it delivered. So it's very ambiguous, single term, single word. Okay. We want a phrase. You say United States or United Kingdom, there's no ambiguity. Okay. That means if we want to do anything, to do entity recognition, topic modeling, something, we have to take the phrase as a basic unit instead of take a word. Okay. But how can we get these phrases? Okay. Of course, some people, a lot of natural language processing people say, we do training, we do parsing, we do, finally we can find the phrases. Essentially, it's people say you need a substantial training data to get phrases. We do not quite like it because it's so expensive. Okay. So can we just, based on the data you give me, massive data, like Europe and twits, you may generate new terms nobody even know. But if it's used popularly, we probably will be able to say this one is a good phrase. Okay. So now I probably can show you previously, okay, there are lots of people working on it. Got some very good progress. Okay. So the first thing is some people are doing topic modeling. They use bigram, trigram, those n-gram model to do the topic model. But these models, you get a very high complexity in the sense you got a long sentence. Anything consecutive, suppose you can construct bigrams. There are so many possible bigrams, trigrams, n-grams. And you calculate all of them, try to find topics. It's very expensive. You think about it. If you got n single words, how many bigrams? You get n squared, right? Because everything can be linked together. And you actually also, not exactly n squared, but it's very, very many. But if you got many more to do all the computation, it's very slow. Okay. Another thing is some people say, I first do topic modeling. I got these things in these single words in the same topic. I merge them. I try these things. For example, you say, suppose you say machine, you say learning, all in the same topic, then machine learning could be a good phrase. But there are, the first thing is, there are lots of things you may not expect they are in the same topic, because if you really do the topic modeling in large corpus, they have several hundred topics. Let's give a simple example, okay? Everybody knows support vector machine. Do you expect that you do the topic modeling, support and vectoring machine will be in the same topic? That Actually, it's very unlikely because the vector likely is a math concept. Machine could be mechanical engineering concept. The support could be a politics thing, like, what's the support of Obama or Trump, right? So unlikely they are in the same topic, then support vector machine will never be able to get together, right? So that's the problem. So we actually work out a new method, one called TopMind by a student, Ahmed Erkishki. He actually is a third year PhD student. He got this paper is very popularly cited, and it's open source. Lots of people are using it. Another one we got also in last year's called SecPhrase or SecPhrase Plus. This paper actually received, within the same month of publication, received the 2015 Europe Dataset Challenge Grand Prize. They give $5,000 to this paper. Okay, simply say they really, really like it. Okay, of course, a year probably for this award they only give one or two, such awards called Grand Prize. Why they are so interested, so excited with this method, I probably can show you. Okay, this method actually, if you really do it, you find it's very fast. How fast it is, I probably can just give you a story. Is during the lunchtime when me and Ahmed, we visited the Army Research Lab, when we got lunch with those Army researchers, one researcher said, I heard, Ahmed, you did something interesting to do the phrase mining. You show me what you can get. He brought his laptop, a MacBook. He just opened it. He said, what do you want? He said, do you have some data inside? He said, oh, I have one data which actually is medical, like a manual, research, not medical rescue manual for people working in Afghanistan. Okay, and one part is English, the other part is Darcy, is written in Afghanistan language, which I do not know anything about it. Even Ahmed could read Arabic, said he did not know most of them. So what we did is we took the English, which is about 200 pages. He said, now I feed this one into my TopMind. Just get a phrase. To everybody's surprise, it took less than 2 seconds. And it generated thousands of phrases, and look at every phrase, the medical terms does make sense. Okay, that simply says that's the speed. Okay, then there are lots of other things I probably can show you, but I probably want to show you some interesting examples. You just see. This is from Europe. Okay. Without anybody trained, without anything, he just feed into this. He actually he did the topic modeling. You look at the results, you probably will see it really makes sense. Like this one, like ice cream, iced tea, French toast, hash brown, frozen yogurt. You probably go to McDonald's, you order those things already. That simply says his software is from Mars, knows nothing about English, knows nothing about human society, and it can give you this result. You think about this. It's not that easy, right? And to him, actually, it's very easy. He's mainly showing this picture. Okay, I would suggest you read this picture, then I probably later I can give you a little on the algorithms or something. Remember, this one is a keynote. I only spend 15 minutes to lecture, but here I definitely go much slower, right? So you probably can see there are lots of very interesting things even down. Those are the things we are going to learn in this class, in this course. Okay. Then hopefully when you learn this, you really got excited. You can work on different things. The nice thing for this one is it does not just work for English. He tried Arabic, and we tried Chinese. People tried Spanish. They all work beautifully. Okay, so we are going to continue this in the next lecture. Thank you. survey can be done in groups. How many? Usually we recommend 2 to 3 people. Usually this. Okay. Yeah, I better break this out.